still there. I know.
Well, there's a lot of gray hair in here.
Goatees and
The ones that have got hair, anyway.
you go underneath, you know, it's all gray goatees and ponytails.
Okay.
Ah,
All right. Welcome, everyone. Tonight we have. Am I in?
You're good.
Tonight, our speaker is Dr. Stephen Walters, and he spent 6 years in the Air Force. He received the Air Force Commendation Medal and a Vietnam veteran. So thank you for your service.
Thank you.
I'm sure I'm not unique here.
Those are the tough times, Vietnam. He 25 years at Bell Labs, Dell, and Telcordia. He's a researcher and a manager. He's a fellow of the IEEE, and he now creates software for astronomers. The topic tonight are Class 1A supernovas, why we like them, how do we find them, and why are they so elusive? So please welcome Dr. Walters.
Thank you. Yeah, no Dr. Walters, please. Okay, it's just Steve. We should have. So before I actually give my talk, I'm going to do something completely different. Those of you who know me know I'm a really avid imager. I guess I've been imaging for 35 years now. And so I've put together a video. We're going to have to dim some of these lights, though. Can we get the lights? Because even I can't see them. So I put together a video of my best images. Okay, here we go. Okay. So here we go. This is not a very long video. Okay, thank you. Yeah, I've always wanted to do a video like that, and finally, I guess about a year or so ago, I did it. So now I force people to watch it, of course. So I know none of you are going to leave, no matter how much time I take, because there's free food, right? And so I've got, this is a perfect audience for me. So tonight the topic is Needle in a Haystack, the search for Class 1A supernova. And I always like to put little cartoons in my talks. I try to put a lot of pictures in my talks and sometimes have a little humor. And the only problem with this one, I saw this and I thought, that's a pretty good picture, you know. It only took you 65, but that's not near enough time. You need about 90 days to find a supernova, and that's assuming you're imaging 400 to 600 galaxies every night on, maybe not every night, but you figure at least 50% of the nights you're imaging and you're checking them. And in roughly 90 days, you can find a supernova if you do that. So it's a pretty arduous task. It's, you know, you need a lot to be able to do this. I'm not going to go into all the detail about what you need, but you can't do this with small telescopes, and you can't do it without. It's just not feasible. You've got to have a fully automated system that takes the pictures at least. So anyway, so what I'm going to tell you about is I'm going to talk about both the past and the present, who finds supernova and how do they go about doing it, in a little bit of detail, not a whole lot. And I'm going to explain to you what a type 1A supernova is. And for a few instants, you're going to be thinking that I'm actually an physicist and I know something about this stuff. And that's totally wrong, okay? But I I got interested in this because of the software that I've did, which is the last thing I'm going to talk about. And so I learned enough about supernova to at least hopefully baffle you with, well, you know what. And so I'm going to talk about why do we want to find them. That's a very important factor. And then I'm going to tell you about a software application that I built that's currently in, it's completed, and we're in the process of trying to acquire supernova with it. There's still some testing and changes and things going on, so it's not, I mean, it's like finished, but there's likely to be things that we're going to do, we're going to change about it. Anyway, so the last part of the talk there is we're going to actually go inside the software, which for some of you is going to be something you're not that interested in. So I'm going to try and whip through that relatively quickly, but I've spent 2 years of my life working on this, so you're just going to have to listen to some of it, okay? So there you go, and I'll try to be gentle. Now let's talk about the history of supernova observations. And of course the Chinese have recorded supernova over the history, beginning, you know, just after Christ. And in 2,000 years, they've recorded 20 supernovas. So that's about one supernova every 100 years or so. It's just not a very quick rate. And of course, we really have no idea. For many of these, we don't know where they were. But many, they recorded the location in the sky. They used a different set of constellations, but you can identify where it was. And some of them have been confirmed that they can find remnants and stuff there, I think a few. These guys were finding them with naked eye, right? They just go out and look at the sky, and they were looking for all kinds of things, of course, and they would see these bright guest stars, they call them. So they were probably the first. Well, I suppose ancient men might have seen supernovas, but they weren't, you know, they weren't really studying or looking for them per se. These guys weren't looking for supernovas either, but they were studying the sky, so they were trying to do some science. And then in 1006, you know, there was a very bright supernova that was observed quite widely around the world and was recorded in all these different places. And so that's the first, I think, to my knowledge, the first supernova that really got a lot of, I'll say, global coverage in terms of people observing it and seeing it. And once again, this was done visually. There were no telescopes then. And then we come along with Mr. Tycho Brahe, who I'm sure most of you know about. And he observed supernova 1572. We really don't know, I mean, he made records of it, but we don't know, I mean, he was just studying it. He studied everything that came along, but of course he was primarily concerned with trying to calculate the orbit of Mars. And so he was making scads of measurements of planets, and Mars in particular. And, but when something like this showed up, and comets as well, I'm sure he would observe them and record his measurements and things. And he also didn't have a telescope, but he recorded positions with astrolabes, huge astrolabes and things like that. And that's Tycho on the right here. Okay, that's Tycho. And you know, I'm not sure who he looks like here. Maybe some of the club members look a little bit like Tycho, I guess. So. But then Kepler, who was working with Tycho, he studied a later supernova, 1604. And once again, it was just something he studied. And this is Kepler down in the bottom center here. And then lastly, from sort of the bygone days, Galileo also studied 1604. And his interest in it was he was trying to find out the distance to it because he wanted to prove, of course, he was trying to prove a solar-centered universe and not an Earth-centered universe. And so if he can find the distance to things, that could help him with his argument. But of course, this supernova is far too far away. It is in the Milky Way, but it's too far away to measure the parallax. So he wasn't successful in it, of course. And that's Galileo down there. And I guess he's got more hair than Jim Rosselli, but probably some resemblance.
Be nice, Steve, because there's 5 people watching you online.
Oh, there are 5 whole people, huh? That's great. You mean I'm not a rock star? Jeez. Okay, so now we move forward in time a bit, and when we talk about people who are trying to observe supernova or find supernova with a telescope, you have to talk about Robert Evans. He was born in 1937, so he's pretty old now, 77, and he has quit hunting for supernova now, I believe. But he was very active. In a period of 50 years, he is the unquestioned king of visual supernova hunters. And you have to understand and appreciate and respect what this guy did. He would go out every night and spend many hours. I don't think he would spend all night long at it. I don't know how many hours he spent. But when he first started, I guess he'd made a list of galaxies that he was going to search, and he would go to the first galaxy and he would look at it and see if there was something there that wasn't there before. So he had to remember what it looked like. And then he would go to the next one. And he just kept adding more and more galaxies and having to remember what it was like, what the galaxies look like. This is the same thing that visual comet hunters do. If you don't know about comet hunters, do a little reading about how people find comets visually. And that's how they do it. They scan the region, usually right after sunset and just before sunrise, looking for comets that would be bright then, that are in places where you don't know where they were. So anyway, in that period of time, he found 41 supernovae in 50 years, okay? And nobody has matched that. I mean, nobody's ever going to either, not 41 found visually. And he did a little bit of work with the imaging system. It wasn't his imaging system or anything, but he was involved with Sighting Springs, the so-called professional observatory. I like to laugh about the professionals because I taught for years at Virginia Tech, and I know professionals are just college professors with a bunch of graduate students and undergraduates, running around doing whatever they feel like. So, but they're paid to do it, so that makes them professionals. Anyway, so he found these 41 supernovae, and during a period of 2 years, he was involved with Sighting Springs, and they gave him access of their 40-inch telescope. And he made about 10,000 observations in those 2 years, okay? Now, notice how many zeros there are. 10,000, not 1,000, not 100. 10,000 observations. And in that time, he found 3 supernovae. So doing this visually, and I'm saying about 9 a year because if you took the 2 years and you figured, well, it was only 55 nights spread over the 2 years, if he had had full-time access to that instrument or some similar instrument, he would have probably found, by my estimates, about 9 a year. And the other way to think about this is that it took 3,333 observations to find each supernova, roughly, okay? So that's how much of your life you're spending doing this. Each one of those observations probably took, not a lot of time, 30 seconds, maybe a minute to sit there and look at it and then move on to the next galaxy. So this is not something you want to do for a living, I don't think. Then in 2005, he managed 6,800 observations with that telescope that's in the picture. That's his 12-inch Newt. And he did a little bit better. He found 4 supernovae during that period, which is about 8 per year, again, if you had more nights, or 1,700 observations per supernova. So he's nearly twice the efficiency, but generally that's just the luck of the draw, okay? Okay, so he was the first discoverer of a type 1b supernova, and I'm going to explain a little bit about the different classes of supernova. Mainly I'm going to focus on 1As, but I will tell you about 1Bs because the pros are now searching for 1Bs. They're very interested in them, as well as 1As. For this, he received the Medal of Order of Australia, the Centenary Medal from the French Astronomique Society, and he's been made an honorary member of the Royal Astronomical Society of Canada. So he got some recognition for his lifetime achievements and accomplishments. Now, you can't talk about supernova hunting without talking about Tim Puckett. How many of you met Tim or know Tim? Yeah, he's a good friend of mine. And Tim has been doing this for a long time, 20 years actually, as of this year. I don't know what month he started, but he started the Puckett Observatory Supernova Search Team, or POST, in 1994, and he found his first supernova that very year, which is pretty good to start in 1 year. Each night he acquires around, it's between 400 to 600. In the summer months you get about 400. In the winter you can get maybe 600 if the clouds don't shut you down. And it's a fully automated 24-inch telescope that he used in his early days. Tim no longer images anymore. He just manages the project nowadays. And anyway, so he collects these images, and they're farmed out to blinkers, we call them, which are people who just download the images, and they already have in their computer a reference library of images of those galaxies. And there's a little piece of software that runs with MaximDL that blinks them and just flips back and forth between them. And if you see something winking at you, then it could be a supernova, or it could be a variable star. It could be an asteroid. There's a lot of things it could be. It could be some bad pixels. And so when somebody in the team finds something, they report it to Tim. They don't report it to the Astronomical Telegram Bureau. And then Tim usually will order a reshoot to get yet another image to see if it's there or if it's moved, which is one way you can eliminate asteroids and things. So that's how this team operates, and they've been very successful. In those 20 years, they found 284 supernova, which is about 14 a year roughly. And this is their exact count for, what is it, 15 years there, I guess, from 2000, well, yeah, 14 years. This is the number of supernova they found each year. So you can see they're averaging about 20 per year, roughly. They've had their best years when they found 37 one year. And it's the luck of the draw, as I said, as to how many you're likely to find. And so it's all manual, really. I mean, the automation of capturing the images. These days, there's a couple of imagers that work with him. Jack Newton out in, I guess Jack's in Phoenix or near Phoenix, I think. And he does most of Tim's imaging now, but there are a couple of other people. And I occasionally have done reshoots for him when they think they found something. He hunts for somebody that's got clear skies that night, and it might not be Jack Newton, so I've done a few reshoots for them. And there's several guys in one of the clubs I belong to out in Pennsylvania, the Hazleton Astronomy Club, who are active in this program. So now for this, Tim received the 2012 Chambliss Award, which is the American Astronomical Society. That's the professional society. It's an award they give to amateurs for contributing to science. And they don't give this award every year. I think they've given it, I think, 6 times. I know Jay Gabaney got one for the tidal streams that he discovered with his images. And what's his name? Not Warner. There's another guy who's at the Society for Astronomical Science, who has been a variable star observer for 50 years or something, and he was given this award as well. And Tim also has his own asteroid that was given or named for him in 2000. So now this method of finding things where you image with an automated system, and then the next day you look through the images, or you can start doing them that evening if you're willing to stay up all night and look at them. But most people do it the next day. And I know there's some guys who I was told might be on the video link who are up in Maine. They're up, I'm sorry?
Doug Rich.
Yeah, Doug Rich. They're up above Acadia there. And so I just want to say hello to them. I was going to put a view graph in here for you, but I just ran out of time, and with this cold and everything, I'm sorry for that. But there are several teams who are doing this kind of search where they'll have one or a few people taking images, and then anywhere from 5 to 10 people blinking the images. So I think Tim has about 20 people involved in his program. And of course, it gets arduous if you've got if you're getting a lot of images and the blinkers don't want to blink. You know, if they've got to work, they got to go to school. You don't necessarily get the throughput that you need to stay on top of the program. Anyway, so this is right now the way amateurs have always done it. They've been doing it like Tim has for 20 years. So now let's look at the history of how many supernovae were found and who found them. And this graph right here shows the professionals and the amateurs. And the amateurs are the dark blue in this graph here. And the pros are this chart, this curve. And you can see the total number of supernovas has immensely risen, okay? If you go back to 1950, amateurs found in 2000, actually here, and before 2000, I think virtually every supernova was found by amateurs, and there weren't that many found, of course. But starting in 2000, amateurs found like 78% of them, but then by 2012, 13 years later, they only count for about 15% of them. And the difference isn't that the amateurs aren't finding supernovae. They're actually finding more supernovae now than before by modest numbers. They went from, I guess 166 down to 159. But in general, the number found is not that. In fact, it's actually a little bit more most years. I think, here's the finds from 2007 to 2012. You can see they had their biggest year was, 12, 13, 4, 20. 7, 8, 9. 2009, they found almost 200 supernovae. But the pros are really outstripping them, okay? And of course, these are the so-called professionals that work at universities. And so we want to ask ourselves, what happened here? Why did this happen? And why did the professionals get so interested in these supernovae? And how did they go about doing it? Because historically, the reason the pros never searched for supernovae is why. Anybody guess why they wouldn't search for them? It's not that they didn't want to find them. Telescope time. Yeah. Right. This is the most inefficient way you can use a telescope. Well, I mean, you can look through one and take more pictures of the Ring Nebula. That's a pretty big waste of a telescope too. But these guys didn't do that, and so we want to know why did they do that, and how did they go about doing it? And the reason they weren't doing it before was you couldn't take the 200 inch and spend all night, every night, imaging 500 or 600 galaxies to find nothing, okay? Because that's what you're going to find almost every night. So it's just not efficient. All right, so what changed this, and why did it change? All right, well, to understand that, we got to talk about 1A supernovas. And this is what, until I read Sky and Telescope this morning when I was getting up, this was the way everyone thought that type 1A supernovas were found. And I'm going to explain it to you, but because I think this may still be the way, but there's a very short little blurb in the latest Sky and Tel magazine that says that they've done some examinations of a field, and this ain't how it happens, okay? So at least that's what I read, okay? Now, I was not completely awake, so maybe. But let's talk about this, because this is definitely still a way it can happen. To understand what's going on here, you need two stars, a normal binary pair of stars. And one of them needs to be a little bit overweight, okay? Not a lot overweight, between 0.8 and like 1.3 solar masses, okay? So it's more or less a normal star, and that'll be the heavier of the two. And then as they age and they move along in their life, this star, the heavier one, is going to gradually turn into a red giant. It's going to consume its fuel. It's going to start cooling off, which makes it swell up, and it's going to get bigger and bigger and bigger, okay? And so when it gets big enough, assuming that this orbital distance is not enormous, which it wouldn't be if they're a binary, it'll start spilling its material. Its atmosphere is going to fall onto this other star, which is going to gobble it up. And the shell of the first star is going to continue to expand, and this is that star now. And this guy over here is absorbing more and more of the gas. And eventually the envelope, the atmosphere of the first star moves away and is just dissipates and moves out. And what you're left with is still a binary pair, but now this one will collapse and become a white dwarf. Now, white dwarfs, if this companion weren't here, that white dwarf would last for an incredibly long time. White dwarfs eventually, they're very compact, They're very massive. Well, they're not massive. They're like roughly, they're about 1.3 solar masses or so. It'll probably be less than what the star started out at. So it's going to be something less than 0.8 and less than 1.3. So it's not a massive star, but it's dense, is what I meant to say. It's incredibly dense because it's very small, and I think I've read that like 1 teaspoon of the material of a white dwarf would weigh more than the Earth. Okay, it's enormously dense material, but it's just going to sit there and gradually cool off, and eventually it will become a black dwarf. How many black dwarfs exist in the universe today? Nobody knows the answer to this. Zero. And why is that? It hadn't been long enough. That's right. They haven't cooled. There are plenty of white dwarfs out there, but it takes longer than the solar system has existed for one to cool down to a black dwarf state. So you've got this white dwarf sitting here in orbit around its old buddy here. And then time marches on, and the buddy starts doing the same thing. He becomes a red dwarf too. He starts to swell up. The only difference is now he spills his material onto the white dwarf. And when a white dwarf reaches 1.4 solar masses, it goes kaboom. That's what they do. All right. And there's going to be 2 magical things about this when we get to the next chart. And when it actually goes critical and becomes a supernova, it basically just cleans everything out in the area, and there's fundamentally nothing left at all of anything. Everything is either moved out, or it's become, cinders. Now, there's 2 special things about these white dwarfs about this supernova. One is white dwarfs have no hydrogen, no helium. Okay, the materials in them are carbon and oxygen, and that's it, basically. I mean, there's some trace materials other than that. So we know exactly the composition of this star, right? It's carbon and it's oxygen. And we know how big it is. How big is it? 1.4 solar masses. It won't get to 1.5 or 1.6. It's going to go kaboom when it gets to 1.4. So it's like me saying, well, here's 100 pounds of TNT, and when you set it off, you're going to get the same thing every time. These things are very repeatable, and that turns out to be the magic in them. So here's the spectrum of a 1A. This is how you identify a 1A, is the hydrogen. Look where it starts. It starts at like 3,700 angstrom, or 3,700 nanometers. Hydrogen is down here at like 600. There's no materials until you get up here. And the other thing unique about a 1A as opposed to a 1B or any of the other types of supernova is that it's missing silicon. It's got an absorption line. It's silicon. So, and there's no hydrogen lines. They have a very sharp peak, and this is not time, okay? Mind you, this is wavelength. So this is the frequency of the light that's coming out of this thing. So this is not time. I'm going to show time in the next chart, and it's going to look a lot like this, of course, but because they go bang and then they die out. But this is the spectrum. So you can look at here, and each one of these things, this represents chemical elements, which now that it's exploded, all kinds of new elements are being created, right? It's creating iron, gold, iridium, platinum, everything you can think of. It just marches up the periodic table, so to speak. So we know what the spectrum, so we can look at this and say, yes, this is a 1A. We know that it is. And if we look at the light curve, this is the light curve. So this is time, and this is its apparent brightness here. Of course, it's faint to start with, and it very rapidly ramps up in a period of about 5 to 7 days, okay? To go from here to the peak is maybe a 10 to 14 day period of time. So they're very fast, and then they decay. And so the total life of this thing in terms of its visibility is about 30 days. So if you want to find 1A supernova, you got to search for them very rapidly. In other words, like every 5 to 7 days, you want to look at the same galaxies again, okay? There's no reason not to. And when you find one, you want to start doing photometry on it immediately. You need to find it before it's reached the peak. If you find one and you're already over here and you're moving down, then you don't know how bright it was at the peak. But here's the thing, is this fellow here, Mark Phillips, who was working at in a Supernova Survey team. He realized that it's the 100 pounds of TNT model. We know what this is. It's carbon and oxygen. It's 1.4 solar masses. So when it explodes, we know its precise, well, I shouldn't say it's precise brightness, but we know how bright it is. Its absolute brightness is mag 19.3, minus 19.3. Now, if you know the absolute brightness of it, you can very easily calculate the distance to it by measuring the apparent brightness here at Earth. So there's a little formula that's going to come up here now. And so you can very easily calculate how far it is to this thing. Now, this gives you a way of checking up on what's the other most commonly used measurement to determine distance for things that are far away. That is, well, no, not parallax. Oh, please, no. You need to study parallax. Read the book. Well, Cepheid variables we'll use in galaxies that are relatively close, but you can't see Cepheid variables in galaxies that are way out there. Redshift, right, redshift. So it gives you a way of checking redshift. So let's do a little calculation. Let's suppose that Mr. Rosselli and his crew, what's the name of the observatory out there? Luna? Luna? Is that your observatory? You guys found a supernova, okay? You found a 1A, and you measured its apparent magnitude at 19.7. So how far away is it? Here's the formula right here. This is the apparent magnitude, what you measure here at Earth, and the big M is the absolute magnitude, which is minus 19.3 that we know from the physics behind that. And you just plug these numbers into the calculation, and you get 631 megaparsecs, which is 2.1 billion light years. So you can use this to measure the distance to things, out to many billions of light years. All right, so, well, so what? I mean, that's a great find, you know. And incidentally, to my knowledge, he's never gotten any recognition for this either, okay? So who cares? Well, these guys were out doing a survey. Rice, Schmidt, and Perlmutter, they were doing a high Z, means high redshift supernova search. And there were two different projects, different groups. I guess Perlmutter was the principal in the supernova cosmology project, and these other guys worked in the high Z supernova search. But they were both teams were doing the same thing. They were measuring redshifts and 1A supernova distances in very distant galaxies and also in nearby galaxies. And they were, like most astronomers in that era, they were trying to argue that the expansion of the universe was slowing down because of gravity. I mean, it kind of, I don't want to say it was the prevailing theory because it was always this open question, but you know, most people thought that the universe from the Big Bang is going to expand, and then it's probably going to collapse again because of gravity, okay? That's what everybody thought. But what they found was that the more distant supernovas were 10 to 15% more distant than redshift said they were. So the supernova measurement said it's further away than the redshift measurement did, which means that the redshift is not accurate at those distances. It's not linear, and that acceleration or that the expansion has accelerated in recent years, and that doesn't mean in the last 5 or 10 years, but in the last many billions of years. So this. Well, when it's a nearby, not very far away, the redshift and the 1A supernova distances agree closely. But when it's far away, they don't agree by as much as 10 to 15%. And these guys got the Nobel Prize in 2011. Notice that the Nobel Committee wasn't in a hurry to give them the award. They did this work in '98, and you know, it took 13 years, as it should, because you want to make sure that this is something that's real, that you know the community of professionals don't find holes in it and disprove it. And so they got the award. They jointly awarded the Nobel Prize for confirming that the expansion of the universe is accelerating. And this is really, by most people's lights, the most important discovery that's ever occurred in cosmology. Some would say in humankind, but I would say fire and the wheel probably are more important than knowing.
Filipinko was on both teams.
You know, maybe. I really don't know for sure. I've never really looked at the constituencies of these teams. But we're going to come to Filipinko, I think, in the very next chart here. So this is definitely important, and part of the reason it's so compelling is that, first of all, we need some way to explain it you know, we were calling it dark energy, but maybe there's just a big ass vacuum cleaner out there somewhere that's vacuuming up the universe and we're being sucked into it. Probably not that, but we need an explanation. And dark energy, when it's all finally figured out, that's really, to me, it's just a placeholder for what, it's a way of explaining the phenomenon, but it's not necessarily what's actually happening. We don't know enough yet. But we need to study this a lot in order to be certain about all of this. And it also enables some things that are kind of sci-fi like multiple universes, parallel universes, an infinite number of universes, and infinite size universes. I mean, this basically just completely destroys everything anybody ever thought about what the universe was, at least mathematically. Now, some of these things might be just wishful fantasies, but if you look at the equations, which I haven't, of course, but supposedly all these things become possible. There's a whole litany of things that we never thought might be possible, but now might be. So, all right, so when this happened, of course, what happened? The professionals wanted to find more supernova, 1A supernovas, and they wanted this for several reasons. One is so they could confirm the findings, and they also so they could explore all these ideas. So they're still on the hunt. So they went and asked for money, and they got it. I mean, when you found the most compelling thing that's ever occurred in cosmology, the National Science Association, the NSA is going to give you, not NSA, NSC is going to give you money. So we have a supernova arms race, and it's still going on. This is the CATE telescope, the Katzmann Automated Imaging Telescope, and it's run by Berkeley, Filipinko. And a typical galaxies produce about one supernova every 100 years, but many of them, probably more than half, can't be seen from here because it's blocked by the core of the galaxy, all the dark, all the dust and junk that's in the core. So how long does it take to find one? And let's look at what the record that we saw what the visual observers and the blinkers did. Let's look at what CATE did. CATE's a 30-inch system, and they image about 70 galaxies per hour, about 600 per night, and they get about 160 nights of clear skies. God, I would die for that. And they take about 100,000 images per year, roughly speaking. And from 98 to 2013, this is their list of finds, and so they're averaging about 60 per year. They found 894 supernova, 1A. Well, and they're just looking for 1As too, incidentally. They're not, but I think these claims here are for all the supernova they find. I think there's about 5% of all supernova are 1As, okay? It's a modest percentage. And that's about 7 times better than Robert Evans, who was just hunting around with his eyeballs, and about 3 times better than Tim Puckett. And so how did they do this? I mean, why are they doing so much better? Is it this telescope? Is it the automation that they have? And so now we want to say, how did they overtake amateurs by such a huge leap, you know, to get almost 9 times more supernova per year than amateurs were doing as a group? And so the money that they got, you look at how they spent the money. And of course, they were able to deploy large aperture. They deployed very fast systems. Some of these, I think the CATE is like an F4 or F3.3 or something like that, very fast systems. And so this aids you in finding faint supernova, getting big instruments, and 30 inches is not huge, okay? But the average supernova is 17.3. Amateurs can easily find a 17.3. It's not that big a challenge. You're not going to do it with a Tasco, 40 millimeter, but you don't have to spend billions. And incidentally, that's the other reason that they got the money for this, is that, what's different about these systems as opposed to the 200-inch in Palomar, the 200-inch Palomar, is this telescope didn't cost millions and millions of dollars, okay? It's very affordable. It's only 30 inches, and it's much more affordable than the big systems. So you're willing to dedicate it to doing these wasted time surveys where you search and search and search and don't find anything, and then finally you do. It also let them, back in '98, we take this for granted now, but they developed software to automate the image acquisition. so that they could just, people could sleep and the telescopes running around all night taking images. Taking an image like 70 galaxies per hour, faster than one per minute. And amateurs also had done this. Amateurs have been running fully automated systems since the late 90s. And so that's not the tiebreaker there. This is the tiebreaker, is they hired an acre of graduate students, computer science students, and said, build me a program that finds little star-shaped images in our pictures that was in this picture last night but wasn't in the picture we took 2 weeks ago. And so, people have gotten masters and PhDs by the train loads for this. And of course, they published everything they did. They don't tell you everything, though. And this is what I'm trying to change, okay? So I've written a program. I've read all those papers, and I know how they do it inside the software. And I've added my own thinking about how to do this in the software. So I've written a program that is going to, I hope, is going to, we're not going to turn the tide around here, okay? But I just want to see amateurs doing better than they are now. This is a screenshot of it. I'm not going to run it for you here. It's far too dangerous to run software in front of an audience because it never works the way it's supposed to. And I'm not going to go through all of this, but it has 3 modes of operation. There's this thing that says abort. We're analyzing a single image, single target of images. There's a batch mode where you can let the scope run all night long and pile the images into a folder, and then the software will scan them and find supernova in it. And then it has the thing, it has what I think is going to be the big differentiators. It has real time. Real time, it sits and monitors a folder, and when a new image shows up, it analyzes it right then. And my program does it in about 20 seconds. Okay, so the pros, because of the way they're doing the image subtraction and some other things, they take about almost an hour to analyze the images. And so this is much, much faster. And and it's being done at the, within seconds of the image showing up in the folder. So now it uses statistics to measure all this stuff, and that's what I'm going to tell you about. Down here at the bottom here, you can see the training statistics, and I'm going to explain some of that. And all this other stuff in here you don't need to know about. But what you see in this picture, I use MaximDL to fetch the pictures, and I use it to display them. And I use the stacking function and a couple of little things. But MaximDL is the wart on the tail on the dog on this thing. All of the real intelligence is in my program. And what you see here is the central region here. That square box is what I call the discovery region, and that's where the program searches for supernova. And this outer region is what I call the training region, and that region is used to train the program on what a supernova looks like. And when we say what it looks like, I'm going to show you some images, but it's a two-dimensional Gaussian shape. It's just a star shape, and that's what we want to see. This boxed star down here is one that's used for PSF matching, and I'm going to explain that. It turns out when you take these images, there's a lot of work you have to do before you ever subtract them. And then it's found a supernova in here, which is a pretty bright one, and it's put hash marks on it. The left hash mark is going through the core of the galaxy, so you don't see it. But it's found a supernova in there. And any area you're interested in reading it, you can go to this website here. That's the Society for Astronomical Science. I gave a paper on it there, which is boringly detailed, and it's on their website. So you can, in fact, you can see the talk, which was terrible. All right, and so the objectives for the program, and I'm going to try and rush through this part because I guess we're okay on time, I think. Is it's going to work down to mag 18 at least, and based on tests I've done, it's working down to mag 20, and if everything is right, it'll work down to 21 almost, 20.5. It's going to do the detection immediately after the image is acquired, so we're not going to wait till the next day. We're going to try and beat the pros at their own game in terms of finding this. And as you're going to see, the way it works, when it finds something, it's going to immediately retask the instrumentation to go and take another image of it. And you'll see why I want to do that. But it'll do that all automatically. And it has a real-time budget of 45 seconds, and it's performing at about 20 seconds right now. So when I first got into this, the way this happened for me is, he said, Steve, can you build a program for me that'll do that? And I said, well, maybe. Let me look at it. So I came home and I thought, well, this, I'd read some papers and Some of it looks complicated, but the basic strategy, which is the same for everybody, take some pictures, you subtract the pictures, and then you look at the difference image, it's called, the subtracted result, and if there's something in there, it's a supernova. Okay, that's how you, so it's nothing to it, right? You just take these pictures and subtract them, but the problem is when you do that, this has only been subtracted in this discovery region, I call it in here, you get lots of stuff. You can actually still see the galaxy in there. You can see this kind of donut-shaped thing in there, and there's like a star-looking thing, another donut down here. You get lots of stuff, and so you start discovering that there's a lot of subtleties to this. And there are actually 3 very complex parts to this problem, and I'm going to try to highlight just what the problem is and a little bit about how to solve it, but I'm not going to try and make you experts on it. The first thing is getting a clean images that you're working with, the new image and the reference image, I call it. And I'm going to explain how I do that, and I'm going to explain how you get a clean subtraction. You can't just subtract the two. It's not nearly that simple. And then you need sophisticated recognition, because no matter how good your data is and how good a subtraction you do, you are still going to have artifacts in there that can look like supernova. They can look like little Gaussian-shaped stars. And this is especially true as you go for fainter and fainter and fainter things. In fact, random noise can line up and look like a Gaussian shape in a point in the image in there. And you'll find it, and you'll think, wow, I found something here. That's why we're going to want 4 images when we do this. All right, so you need some very sophisticated recognition. All right, so here's how we get to clean images. We take 2 reference images, and when we first thought about this, boy, that's going to be a showstopper, because, you know, that means wasting a lot of time taking these reference images. But if you're searching for 1As, you're going to shoot the same galaxies every 5 to 7 days anyway. So you're just going to be loaded with images of those galaxies. So it's really not a big deal if you're wanting 1As or 1Bs. And in all of these supernovae, you'd like to find them early, which means shooting them frequently. So it's really not a problem to have 2 references. Oh, thank you, thank you. Maybe I can recover a little. Oh, that hurts so good. All right, so we'll start with 2, and then at a later date, we'll take what I call the new image. So we're going to have 2 refs and 1 new, and I'm going to duplicate the new image, and all that's going to be clear why I'm doing that in a minute. And I'm going to do this signal processing thing, which all of you, how many of you are imagers and do stacking and all that jazz? Oh, not too many. Okay, well, I'll try not to bore you, but the first thing you do is you align these images and you remove gradients from them, because there's going to be gradients from the moon in these things. We shoot all year, you know, we don't ignore the moon, or we don't shut down for the moon. There'll be clouds, there's all kinds of crap in these images, but you'll do as much as to clean up the individual images as you can. Then, if you know what median combine is, medium stacking has a very nice property. We're going to stack 3 images in each instance. I'm going to take the 2 reference images here, the red lines, and I'm going to combine those 2 with the first one of the new images. And for the moment, mentally think that these are going to be 2 different images eventually, but right now it's the same image. So when we do the median combine, if there is a supernova here, it ain't going to show up over here. It's going to be eliminated, because you got 2 out of 3. Oh, I'm sorry. Oh, God. Yeah, man. I'm sick. I'm a sick man. Show mercy. I'm sorry. So the red lines are one of the median combines. We're going to combine the 2 reference images with the first one of these 2 images. And when you do that, if there'll be no supernova for sure in this, because there's no supernova in the reference images. And if there is one here, it isn't going to survive the median combine, because it's the odd man out. It's 2 out of 3 isn't there. So, and you do the same thing again with the same 2 reference images, but with the other new image. And right now it's the same 2 images, but in a minute we're gonna fix that. Then you do it again with the new images. You combine the 2 new images with the first reference, and that gets you another new image. Now in this image, if there's a supernova down here in these 2 images, it's going to appear here. It'll survive the combination process. And you do the same thing again here. And now these 2 images, if there is a supernova, it's going to be in both of them. Then you do a mean combine to combine the 2 references to create what I call the reference, the master reference, and you combine the two news to get a clean new. Now, if you find something, if you go through all the rest of the faulty raw I'm going to explain to you, and you think you found a supernova, what we call a PSN, a possible supernova, if you found a PSN, then you're going to take a second image, which now we have two new images here, and it's a second one. And you'll wait 30 minutes to an hour later. And the reason you do that is so if there's an asteroid, it moves. Why do we want to do that? Because when we do the median combine, if it was an asteroid and it moved, it's not going to survive into the median stacking process. Now, but if it's really a supernova, it's going to be in the same place in both images, and it'll be there. Now, so that's the first thing that's sort of magic about this algorithm. And I don't think anybody's doing this but me. I haven't found anybody that says they're doing it. And because you're using all four images are used to produce both of these over here. These two, this reference image has pixels, so to speak, from all four of these images in it, okay? And the beauty of this is you get, first of all, just the stacking process improves the signal-to-noise ratio, so you have a cleaner image, and the noise characteristics of these images are made more homogenized. They'll be very similar. That you might have noisy new images and nice clean reference images, but when you stack them, if you don't do something like this, you're going to have noisy images and clean images. These images now all will look very similar as far as their noise characteristics. And there will be no transients in there, no bad pixels, no cosmic ray hits, no asteroids. All that is eliminated unless you got a really slow moving asteroid, okay? So this is how we get clean images. And so now we're going to take the reference image and the new image, and we're going to try and subtract them. Now, as I say here, reality is not ideal, and nature is not kind. Here's what a star looks like when you've got good seeing. Has anyone ever seen a star like that in New Jersey or Pennsylvania or anywhere? I mean, ours don't look like that in Pennsylvania. They look more like this, bad seeing. Now, what's the difference here? There's two. Everybody knows that the bad seeing stars are fatter, right? They're bigger in diameter. But what's the other difference?
The slope is slightly different?
Well, it's shorter. The same amount of flux is coming in. The number of photons hadn't changed, but now it's spread over a bigger area, so the peak is lower, okay? So it'll have a lower peak than this one. Now, it's not, you have to figure that out here by looking at the scales. You know, this is like 50,000, this is 20,000. So now when you subtract these images, what happens, okay? Well, if you have a new image that has bad seeing, and you subtract that from a that has, or sorry, it's the other way around, subtract a good seeing reference from a bad seeing new, what do you get? A donut, right? Because this is brighter than that, so when it subtracts from the center, you actually go negative. You get a negative peak in the center, and then all of this crud that's around it, because the star is fat, well, there's nothing here to subtract from it much, so it survives, and you've got this donut shape, okay? That's the difference image. So, well, as you're going to hear, this turns out not to be horrible because it's not hard to tell the difference between this and something that's shaped like a star when we start looking at how do we recognize these things. But it's still not good to have them. Now, here's the evil, the great evil. What if it's the other way around? If you have a crappy reference image and you got better images tonight and you subtract them, what do you get? You get something that looks just like a star. And the reason is because you subtract this, so the outer part goes negative a little bit, and you can see that, but it's not going to be deeply negative, and we don't even care about that because that's surrounding the star. But the center, this is a lower peak value, so when you subtract it from this higher peak value, you get this. That's what's left. And so you get this thing that looks just like a star. I mean, it's exactly like a star. And so you really hate to see this. Of course, you hate to see both of this. So here's what we're going to do, is we're going to match the stars in the two images by blurring the good image to make it match the bad image. Oh, God, that just horrifies me to do that to an image, but that's what we're going to do. So this is called convolution, and we pick a well-shaped star. We find a star that's nowhere close to saturation, and it's got a good Gaussian shape to it, and then we repeatedly blur it with different blurring factors. It's a binary search that I use, successive approximation, to find a blurring factor that makes the full width half max of that star match its buddy or the same star in the other image so that they have the same full width half max. And once you found, and you can do this very rapidly because you're not blurring the whole image, we're just blurring the region right around that star. So it runs very fast. And then you blur the entire image. And now you've matched the stars in the two images. They'll have the same diameters, and they will tend to have almost the same peaks, but not quite the same, because you still have to scale the background and the brightness of the images, because there's clouds, there's moonlight, there's all kinds of evil things, and we're going to have to adjust with a kind of a, I used to have a, I guess it's the other technical paper, it's like a bilinear stretch. There's 2 points that I pick. I match the backgrounds perfectly, and I match this what I call the PSF star, the star that was used for the convolution. I match the brightnesses exactly at that point, at that brightness level. And now you can finally subtract the image, and this really works. You can see what you got here. This is a very clean subtraction compared to what you saw before. You may not appreciate how much better it is, but I can tell you when I finally saw one of these, my lights went off. Now, as I said, as you go to fainter and fainter supernova, you will still find stuff in here. You know, if you start looking in there deeper and deeper, you'll find stuff. All right, so now we got to be able, so we still have to be able to recognize the difference. We got to be able to tell the sheep from the goats. And so a true supernova, these things are going to be noisy because there's noise in these images. They're not going to be this nice mathematical shape. They'll be close, but there's going to be noise on them. So this might be a real supernova, and this might be a residual that's left over from a bad, poor subtraction. The PSF star might not be as well shaped as we thought it was, and so forth. And you may have residuals that are just noise, you know, but that could actually kind of look like one. So in my program, I measure 4 properties of the shape of the star. I measure what's called flow, which is similar to flux. That's how bright the star is. I measure the size, which is similar to full width half max. That's more or less the diameter of the star. And I measure the fit. The fit is if you construct a radial profile by like wrapping the star around to where it's just a one-dimensional curve, it should be a nice Gaussian shape. And I measure how Gaussian shaped it really is. And then I do a 2-dimensional check on of what I call tilt, which is asymmetry in the image. Is it asymmetric? And so this is what I measure. I'll never tell anyone how I do it because that's the secret sauce in this program. These calculations have to be used about 500,000 times for each target, okay? So they have to execute very rapidly. All right, so now this is how we're going to tell the difference between supernova, things that are shaped like that, and residuals, which are shaped like this or this. But to do it, and we call this thing the classifier, to do it, we have to know what are the values. I mean, what's the flow supposed to be? What does the flow look? What is the value for flow in the supernova? And what is the size? What does it look like? So here's how we do that: is we train the classifier by inserting artificial supernova throughout the image, and then we go with the classifier to each site and we measure those properties, and we calculate the mean, standard deviation, min, max, and the range that we're going to allow detection over for the 4 properties. And so we basically are going to measure the statistics of what these things look like in images, okay? And so we're going to know how bright they are, how big around they are, and how Gaussian shaped they are. And we shouldn't see big standard deviations here. You can see they're quite small because it's just a modest amount of noise. Then we're going to scan the image, and when we do, we're going to find things that the classifier says, oh, I found something. Well, maybe it has found something, but we're not going to trust it just yet. What we do is we scan, and when we find something that it thinks is a supernova, then the first thing we do, we're looking in the difference image, mind you, okay? We look at the new image and the reference image at that same position. And if we see a star in the new image and a star in the reference image, then this thing is not a supernova. It's a residual from subtracting those things. But if we see a star in the new image but not in the reference image, now maybe something's going on there. So what do we do when we find one of these residuals that isn't a star, that we think is a product, a result of subtraction, is we're going to use what I call the Black and Decker method on it. We don't really care. I mean, at one point I was trying to actually like remove it from the image, so when I scanned I wouldn't find them. But then I realized that's not necessary. All I need is to drill a hole in it. Oh, this was the example of finding it. I just drill a hole in it, and I make the hole big enough so that when the classifier measures it, it doesn't find it anymore. It doesn't think it's a supernova. And as soon as you start, punching holes in these things, then the classifier says that's not a supernova. It doesn't stop on it anymore. So once you've done this to all the residuals that you can find that way, now you can turn it loose and actually search and scan for real supernova. Okay. And so you scan the discovery region. This is the star that was used for the blurring, to figure out how much blurring to apply to the image. And the training was done inside of that area, and it's found a very faint supernova in here. In fact, it's so faint you can hardly see it. And now when you first run this thing, when we run this in New Mexico, we have two reference images, but we take one new image and we check it. And we find things that the program thinks is a possible supernova. So then we take another image within the next 30 minutes or so, and then we do it with 4 images, and like 98, 99% of the time it says, I don't know what we were all excited about, that's not a supernova. And the reasons for this are twofold. One thing is it might be like an asteroid that's moving, and it looked like a supernova in the first image, but now when we take another picture, it's gone. It's not in there anymore. And the other is because we have almost no noise in these images once you've got 4. When you've only got 3, all the garbage that's in that one new image survives into the final images. You get cosmic ray strikes are in there, bad pixels are in there. Nothing is eliminated really. Well, I shouldn't say nothing, but very little is eliminated. So you got a nice clean image. Now, if you did this, if you find something when you take that second image, it's party time, baby. Okay, and we will actually, what we'll really do before we break out the champagne, is we'll task the system to start doing photometry while the champagne, and we'll party it up. So far, all of our tests have been done with, we deployed it in August, and there's a second site coming online next spring that he's building that's going to be in the Tehachapi's in California. And of course, we haven't found any supernova, but we've imaged about 1,500 galaxies, anywhere from 2 to 8 times so far. He's got a pretty, of the 1,500, which is the ones that eventually there's going to be 14,000 galaxies in the catalog, and there'll be 28,000 images in the reference library. So the program includes a lot of code, some functions for maintaining the library. Like it'll automatically replace bad images in the reference library with better ones that you took last night, for example, and it'll audit them and check the characteristics of them. And you can change how good a quality image you want to have placed in the library. There's control for that. So at any rate, we haven't actually found anything yet. We found an asteroid which got eliminated when this 4th picture got taken. But it looks good. I mean, it's still too soon to get, to really get excited. But just doing tests, we can detect down to mag 20, even 20.5 if the images are very clean. If it's isolated from the galaxy, if it's not buried in the guts of the galaxy, we can find these things down to very faint magnitudes. It'll do 19.5 if it's in the arms of the galaxy. And we've even found mag 19 that are in the core, which you can't see at all. I mean, a blinker is never going to see these last 2 images. They won't see a 19.5 that's in the arms or a 19 that's in the core. Now I'm going to play a little video. I call it my supernova discoveries. These are all just images that were where I put fake supernova in there and ran them to see if it could find them. And of course, I'm not showing the ones where it didn't find them. So we've got a little music here too, and then that'll be the end of the talk. I love Bach. Some of these, try to spot them. See, like that one, I don't think you'd ever see it. All right. Thank you.
So actually, most of what you said makes sense.
Makes sense to you.
But when
Read the paper if you like. In fact, I was going to bring some
Well,
copies.
I want to talk to you afterwards, but
Sure.
I just want to ask some general questions because some of the guys here might. When you say training, to me
Yeah.
that speaks of AI and neural nets. Is
Yeah,
that what you
well,
mean when you say training or something
yeah,
different?
no, it's not quite like, it's not AI and neural nets for sure.
Okay.
But we've got this classifier that just measures those 4 values, okay?
The secret for values.
Well, no, the 4 values aren't secret,
you
but
said how they do it.
how it does it.
Yeah.
That's what you can ask me all you want about that, and I'll say no thanks.
that's okay.
Because it'd be very hard to duplicate that part of the code. It's really, well, anyhow, so the training is, when you want to hunt for these things, you got to remember the image is noise. Okay, this training is done every image every time. It's not done once and then you use those values forever. Every target, when you image that 3rd or 4th image, it trains because the noise characteristics are different every time, and that affects everything that you see in there, the standard deviations of these things. So we put fake supernova in there, then we put them in at the brightness that is the faintest value you hope to discover. Okay, so if you want to discover mag 18, you put mag 18 supernova in there. And the program has a routine for doing that. And it puts nice, perfectly little shapes in it, but it's embedding them in the noisy images and in all the other crud that's in there, because there's galaxies, there's everywhere. And then you go to each one of them and you measure it with the classifier, and you calculate the mean and standard deviation of those properties, everything. So that's the training. So now, so you know what a supernova should look like in that image, and that's what the training, and it really is. It's considered training. It's not neural net training, but it's the same concept. It's just that you're doing it for a statistical Bayesian classifier is what you do. And there's books written about the Bayesian classifier. So this is basically that. It's very classic in that regard. These in so that your statistics know about the noise in this image, not just some image you took years ago. It's this very set of images, and then that gives you a better chance of finding the real thing in there. So that's what that's about.
Now, you talked about the 20 seconds. Are you trying to shave more time off of that?
No.
You're fine at the 20
In fact,
seconds.
I'm probably going to be adding more functionality to it, so it'll work even better. We have very few false positives once you do this 4th image, but we'd like to have fewer false positives with 3 images because it wastes telescope time. We actually have to send the telescope off to take the 4th image, and right now we're getting about, I think, maybe 9 or 10%, something like that. It's not a huge number, but it's enough. We'd like to do better with 3 images if we can.
You'd rather get rid of false positives, and you'd rather cut down on the false positives and get rid of the image.
But without missing one,
No, I hear you.
missing the real thing, and it's a real balancing act too. Yes.
What would happen, I'm just curious, with the resolution of cameras going up and so forth, if you actually spotted the progenitor star?
Well, it's not going to be bright enough. Unless it's near you, the progenitor stars are not going to be at minus 19.3. I mean, that's an incredibly bright source. They rival quasars, I think. So unless it's near you, I mean, there are, let me just say, this article I mentioned in Sky and Tel that said maybe this isn't the way they're generated, that the binary thing. That's what they did. They found a progenitor situation that where they said, this isn't going to do what everybody thinks they're going to do. And I don't know enough about. I mean, I want to read their paper because I just saw this morning, and I've been running ragged all day, so I haven't tried to find the paper and read it, but I will. And so apparently there's something that they think they've found, and it is from imaging a progenitor. They did do that. And everyone's thought that there are other ways you can get it. No one is saying this is the only way you can get a Class 1A, but this is the one way that people think this is a clear case that it would create a 1A. And it's a very common situation of binaries. Binaries are very common, and stellar masses between 0.3 and 1.3, or 0.8 and 1.3 are also quite common, I think. So, another programming question.
Sorry. Okay. How do you know that they're not giving away the software, the ones that, you know, the...
Oh,
How do you know? I mean,
I know why that is.
Okay, did
All
somebody
right.
actually write them and ask them and they said no up front? Or?
Yeah, and well, I didn't do that, but I know the answer, and the reason they won't give it to you is the funding.
Yeah, but it's government funding. I mean,
Yes, but they're competing for it.
But my
Schools-
understanding is if you want, like if NASA writes software, I can go out to NASA.gov and get tons of free software.
Yeah, that's
Government-
NASA. The university doesn't have to do that.
But aren't they getting paid by government funds, which is...
Well, you'd have to look into that because I know this. They will not give you the software, and the reason, because Puckett has asked for it.
Okay, so
And they say,
did ask for it.
oh, yeah, you know, read our papers, you know, see if you really want this. And the facts are that you probably couldn't use it anyway because these guys write in strange languages and they
All right,
run,
strange languages.
yeah, and you know, it's not, and it's very custom for that system, for that telescope. It's not generalized. This is pretty generic, you know, but mainly the reason they don't want to give it to you is because when they go, they say, we found 246 supernova last year, and that's 100 more than these other guys, so you need to give us more money and less to them. That's what they do. I mean, that's the argument.
Okay, no,
And they're content. The supernova arms race is still going on. I should have said something when I had the chart up there, but now the focus, they're still looking for 1As, but they also want to find 1Bs, and I don't completely understand why, but there's some science associated with 1Bs, and they're hoping this will give them more insight into the expansion of the universe and dark energy and all of this stuff. So there's something about 1Bs that they're interested in, so they're hunting for them now too. Yes, we'll start with you.
Has anyone done any statistical analysis on the magnitudes? Like, for example, are type 1As in magnitude range 14 to 16 more likely to be discovered than 19 to 20?
Well, let's see. First of all, the 1As are all minus 19 absolute brightness, all of them. So how bright are they here? Well, that depends on how far away they are, okay?
Right.
So now you're talking about the distance that you're searching at. So if you're searching for real high redshift, you know, very faint things, they're going to be very faint here. I mean, in my little example for NJAA supernova that you found yesterday, that was mag 19 here. That was the apparent bright 19.7 or whatever I wrote down. And so that's pretty faint. And whether you can detect it or not means aperture. The more money you spend on aperture, the fainter stars you'll find, and the software. And that's better software will do an equal job with a smaller telescope than crappy software will do with a big one, okay? Because the signal noise ratio is better with the big one, so you can be, you know, your software doesn't have to work as well, but with a small one, it's got to work better. But of course, what you want is the best software you can build, and you use it all the time, no matter. You don't go out and get cruddy software so you can use big telescope. But anyway, does that answer the question? I'm kind of lost.
I guess really the question is are the
Well,
professional...
I can tell you this, that the magnitude of the average supernova that's found, full stop, I mean, of all supernovae that are found, if you look at the CBAT list, 17.3. Okay. That's the average, okay? And there's, you know, half of them are brighter than that and half are fainter. You will see them on the list down to mag 23. Okay, that's pretty faint. I don't ever hope to detect a mag 23 here. And you wouldn't do that with a 20 or 25 inch, 24 inch telescope. It'd be impossible. You're not going to detect mag 23. It's just too noisy. The image is going to be too noisy even with a big instrument. Those very faint things are being done kind of as an after fact with Palomar and other big systems. The Hubble has found a few. They don't do it. They don't start out to do it, but it's like, you know, it's a sunny day. It happens, so they get credit for it. And 1As are about, I think I mentioned this, they're about 5% of all the supernova, roughly. And I think 1Bs are about 17%. So on that order. Now, you were next.
I was going to ask about, you had a curve up there showing the decline and the rise of supernova intensity over time.
Right.
Is that the same for all of them? In exactly the same shape?
Well, I think for 1As it is,
Yeah,
but
okay.
not for all supernovae. No.
Okay. For the
They're
1As.
all similar. I mean, it's not like some of them last for decades and some last for just hours. But you know, you figure 30 to 90 days, I think, is kind of the range of these
And
things.
is
Once, yep.
Is that also for the same colors, or?
Well, the other supernova have different spectral characteristics. I mean, the thing that's unique about 1A and 1B, and I guess there's 1Cs also, is they have no hydrogen helium emission lines in them, none at all. The other supernova all have that. The difference between 1A and 1B is between 1A is the only supernova that has nothing at the silicon line.
Okay, so
The others show some.
when the procedure in terms of when they actually do this, what kind of color filters are they using?
Oh, for the spectrum?
No, just to, in other words, at the.
You
just
mean to
taking the
detect the
image,
supernova?
to
Oh,
the
it's just,
image.
man, you shoot through a clear filter.
Clear,
You
okay.
just get all the photons you can to bring down the signal to noise ratio.
So those curves are for clear filter.
Well, yeah, I mean, I don't think anybody's using special bandpass filters for this, not to my knowledge, because it's a photon game. You got to get as many as you can, and you don't care what wavelengths they're at. And you can't really tell the difference, at least not with small systems like these 30-inch even. I don't think you can tell much difference between these things in terms of the spectrum that they're emitting. In other words, it's a stronger emitter down towards the bottom of that, which would be the oxygen, I guess, or no, that would be the carbon. But no, because this is after it's exploded. I'm sorry, I keep screwing that up in my head. So there's just almost everything you could think of is in there in the emission lines, except it doesn't have the silicon. Now, how bright it is in there, that varies a little bit from 1A to 1A, but they're all missing the silicon, and they're generally shaped like that. But it's not to say that it's the same exact amount of, because it's after it's exploded. Okay, now before it explodes, the white dwarf, if we could see it, it's just carbon and oxygen. But that's not what we're seeing. We're seeing the explosion, which it's producing iron and gold and everything. Right? There was another hand. Yes.
Yeah. Okay, this is out of my normal area, but okay, you're trying to get what I'm going to say is a normalized picture when you try and say so you can track everything out, and you're using a star up in your field that's like in the training area.
Yeah.
Would it help if you used, like, I know where they shoot up a laser beam to generate a fake star? Would that kind of help in any way? Or has anybody tried that? I know it's used.
Well,
for
the problem is it has to be in both all the images that you got. I guess, I mean, you could do that. I'd have to think about that, because that would work, because all you're trying to do is measure scene, basically. That's what
Yeah.
you're doing. And so, yeah, you could do that.
Because you have a constant, right? You know the
Yeah.
frequency, you know the amplitude,
Yeah.
no matter, so.
Yeah.
I just wondered, because I'm not saying, I wouldn't do it if needed, because I wouldn't have the money, but this guy sounds like he's got money. It's like, all right,
Well,
for
yeah, no, I
$1,000.
think if you're going to shine lasers into the sky, you have to get permits.
Oh, I know that.
There's
but-
airlines.
No, I know that, but
Yeah.
I'm saying, you're trying to cut that one picture.
Well, this
out.
guy he ain't important enough to get that permit.
Yeah, but it's the one depending upon where you put the telescope at, though. You know
Yeah.
what I'm saying? Yeah, all right.
Jim, we need to knock off.
No, two questions, please.
Oh, yes. Oh, you.
Number one, the effect of signal to noise ratio on capture versus your time, doing it from here in New Jersey in our wonderful skies versus Sierra Nevada or New Mexico skies. That's question one. And question two is the field of view, the frame that you had put up. It seems like the field of view was, let me say, all of the objects, the targets that you had in the field of view were framed accordingly. So the majority of the sensor wasn't used. You're just taking the core area and using the training on the outside.
Yeah.
Is that for speed and
Yeah.
process?
Yeah, the basic strategy with the software to limit the real time is you don't process something that if you don't have to, okay? And the processing goes up by the square of those areas, right? If you make it, I think these are, see, the training region is 500 pixels by 500 pixels, and the search region is 300 by 300, okay? And this is on a camera that's a 16 megapixel camera, okay? So we're using a very small amount of the field. But as long as the galaxy fits in there, that's all we care about. I mean, you're not going to find a supernova out here unless it's in another, like this might have one in it, the galaxy. But at some point you got to say, well, we can't, if we were to test the entire image that we hear, we wouldn't do it in 20 seconds. I don't know what the time would be, but it'd probably be.
All right, thank you
That's
very
great.
much. for
Yep,
your
you're very
input.
welcome.
Thank you. I'm gonna stop the streaming, we're going offline. I don't even know what are the skies like, guys? Good. Good? That's a good thing. That's very cool.
Did someone turn off Newark and so forth?
If you have, Steve has been gracious with his time this evening. I know he's got a sore throat and he's working through it. I don't want to limit him from answering questions, but please, if you do, it's a great opportunity. He's here.
It's a great opportunity to get sick too, so come on up.
Right.